Hi there, and thanks for coming. So, as Stefano mentioned, I'm Brendan Dolan-Gavitt. This is actually my first time speaking at Black Hat, and I'm really happy to be here. For the past 10 years, I was actually a professor at NYU doing software security and a bit of AI on the side, and now it looks like it's the other way around. That seems to be the way of the world. So as of this month, am jumping ship into industry, doing Expo full-time. Other things you might have seen before, way back in the dawn of time, I was a core contributor to Volatility, the memory forensics framework. Back at Black Hat 2022, we had some work here on the security of GitHub Copilot, asleep at the keyboard. And complementing that, I also, for a while, ran an open source project that let you locally host your own version of GitHub Copilot. So why are we here today? Well, I'm here today to tell you that there is a specter haunting AI offensive security. And that specter is the specter of false positives. So if you recognize these two blog posts up here, these are both from a very frazzled and much abused curl developer, Daniel Stenberg, who has been cursed to receive every AI-generated false positive report about security issues in libcurl on the internet. So there's a Twitter feed that will show you every report to HackerOne that gets publicly disclosed. And if you follow it for a while, you notice that like 2/3 of them are false positive reports to curl. And you start to feel really bad for this guy. Okay? And so the typical case is someone takes the curl source code, they copy and paste it into ChatGPT. It tells them, hey, yes, there's a serious security issue I found here. And it gives this very convincing, very eloquent, and totally fake explanation of the security problem. Okay? And so this is one of the major problems with trying to naively use AI for offensive security right now, right? That these models have been trained to be very helpful, and they interpret being very helpful as the user really wants me to find a vulnerability here, okay? But they're not great at having good grounding in reality. So when you hear this, one of the first things you might think is, OK, don't have great grounding in reality. Well, this is 2025. This is the year of agents. I am going to use an agent, and it will run tools that let it talk to real websites or interact with real software. And maybe that will help me with false positives, right? Because it will run a command, it will get some error back, and it will think, OK, then that must not be a real vulnerability, and it will now only produce true positives. OK, so I don't know to what extent people have tried using agents to do offensive security research here, but this unfortunately does not work very well. OK, so maybe a little bit hard to see right here, so let's zoom in a bit. And if you've worked in Bash, as I have for a somewhat disturbing amount of my life, about 25 years now, you'll notice right away that there's a quoting issue here, right? That when it created this variable, it meant to do a command injection on the server using backticks. But because it used double quotes instead of single quotes, it ended up putting its own password file into the request, and then the server just reflected it back, and it thought that it had managed to read the server's password file. Okay? And so this kind of problem is super pervasive. Even when the models aren't making things up entirely, they're very, very good at convincing themselves that there's a problem there when there's not. Another kind of classic example is it will do something like see some random network delays from the server and assume that there must be a timing-based channel that it can exploit, right? So all of these are problems that are very hard to surmount if you're just using AI to validate itself. right? If you're basically letting it grade its own homework. So this problem also gets much worse at scale, right? So let's do a little bit of remedial statistics, a pop quiz. This is one that I hope everyone gets right off the bat, but actually if you don't, you're in very good company. Lots and lots of even very experienced professionals, like say doctors, get this one wrong. Okay, so let's do a little quiz. We've got a medical test that's 99% accurate. This is great, right? What we're saying here is that when we test a population of individuals that really have the disease, 99% of the time it says returns true. It says you have the disease. And when you're testing a population of individuals that don't, 99% of the time it will correctly say, no, you don't. But there's one small catch here. This disease is very rare in the population. Okay? Only 1 in 10,000 people have it. Right? So you go to the doctor, and the doctor gives you a test result, and they say, you've just tested positive for this disease. How worried should you be? What's the probability that you actually have this disease? I heard a 1%, so good job. You've seen this example before. Or you're very good at doing Bayesian math in your head. Yeah. So if you take basic application of Bayes' theorem, look at the conditional probability. I'm skipping over the calculation here because I want people to be awake for the rest of the talk. But it turns out that even if you test positive, because the base rate is so low, right, because this disease is quite rare, the prior probability that you actually have the disease is very low, and therefore, even after the test, even a very accurate test doesn't actually add very much evidence. Okay? So what's the implication here? That if you're testing for something very, very rare, you need extremely accurate tests in order to avoid this sort of curse of the base rate fallacy. Okay? And so I'm definitely not the first person to have noticed that this applies to security. The first person I know of to have done that was Stefan Axelson, way back, I believe in the 90s, who had this great paper on the base rate fallacy and its implications for the difficulty of intrusion detection. But it applies here, right? And now I know many of us are security people, and we say, well, come on, security vulnerabilities are not rare, right? They're everywhere. But if you think about it in terms of number of lines of code, for example, how much of that code is actually vulnerable, it's a fairly rare event, right? And so now if you consider ChatGPT as your detector, and you apply it to code indiscriminately, you're going to get lots and lots of false positives. OK. So really, at the end of the day, the only solution to this is to start driving false positive rates down, right? Demanding very, very accurate tests. Okay? So at the moment, LLMs cannot do that for us, right? I don't want to say that they will never be able to do this for us, because, for example, just last week, both Google and OpenAI managed to win the International Math Olympiad gold medal. And they did so using language models that were verifying their own answers. So they weren't relying on deterministic tools like theorem provers. Instead, they were actually looking and critiquing their own output and then settling on an answer. And so potentially, maybe a couple of years down the road, we'll be able to actually use language models out of the box to verify vulnerabilities. But for today, and for the rest of this talk, I want to sort of propose and argue for a different way, which is using essentially non-AI deterministic code to validate vulnerabilities. OK. So what's our toolbox going to look like? So our two big weapons in this arsenal are going to be canaries, as you might know them better as things like CTF flags. So these are basically hard-to-guess strings that you can plant in places where you think that an attacker should never be able to get. Okay? So for example, if I want to go looking for remote code execution or arbitrary file read vulnerabilities, I can plant a canary on the server's file system and then send AI agents after it. Okay? And unless the agent can guess a UUID, which, let me say, is not going to happen, then if it manages to retrieve that flag, that means that it really has found a vulnerability that lets it read that file off the server's file system. And by extension, generally means it can read any file off the server's file system. Okay? So that's one way of doing things. And we'll talk about some pros and cons. The other is that we can try to use deterministic validation from evidence provided by the model. Okay? And so what we're going to do here is we say that if you have really managed to exploit a vulnerability of a particular type, then it must be the case that you can provide me with some evidence that you've done so, right? And this happens all the time with humans doing bug bounty research. You don't just say, yeah, I found a vulnerability, and the company says, great, here's $10,000. Doesn't happen. I've tried. What actually happens is that they say, well, OK, if you've found a security vulnerability, give us some evidence. And then you give them, for example, all of their AWS tokens. And they say, oh, yes, you shouldn't have been able to get those. I believe you now. OK? So this kind of thing, we can basically, for specific vulnerability types, we can try to come up with what evidence we should demand from the model that we can check deterministically that will prove to us that it really found a vulnerability. And I'll talk about a few ways that we can do that. So one thing that you'll notice is that, that I think is kind of fun is that we've kind of gamified the problem as well here, right? We've taken this problem of offensive security, and we've turned it into a series of capture the flag challenges. And I think that's quite fun. And it turns out that this has other benefits as well. So one thing is that capture the flag challenges always have a solution, right? And so if you tell the model that it's solving a capture the flag challenge, it tries very, very hard to find a vulnerability because it is certain that it must exist. Okay? And so this is really good because another thing that models are often pretty bad at is judging when they've tried hard enough, when they've really explored all the possibilities. So with these kind of two approaches in mind, let's look at maybe a sort of map of validator space. Okay? So I've divided this up into kind of two axes. One axis is whether you require some kind of cooperation from the target that you're trying to attack, right? And I don't mean cooperation here in the sense that, you know, they let you in and you can just read whatever you want. I just mean that they're willing to do some setup for you, or you can do some setup because this is, for example, an open source application. Okay? And so the other axis is whether there's some manual intervention that you have to do, some setup that you have to do beforehand. So the type that require manual intervention, this is things like planting canaries somewhere in the application logic. And this is really nice for sort of targeted vulnerability hunting that can go after even things like business logic vulnerabilities. And so we'll talk a little bit later about a kind of fun authorization bypass in a project that we found using this kind of technique. Okay? The other are things where you still require some target cooperation, but the process of setting it up can be fully automated. Okay? And so this is the case, for example, if you've got open source software, maybe some Docker containers, you can stand up the application automatically. You can go and plant canaries and then attack it automatically. Okay? And so we've done this with some large-scale scans of Docker Hub looking for web applications. And I'll talk a little bit about that later on in the talk. But for now, we can just note that we can do things like look for SSRF vulnerabilities by standing up an internal web server. We can do things like planting a canary somewhere on the server's file system. And we can even do things like add canaries to an SQL database if it uses one. Okay? The last category is maybe the most interesting. Okay? And I suspect that a lot of people are in the room because they heard that we got to the #1 spot on HackerOne in the United States, at least in the combined VDP plus bug bounty category. And if you look at these other quadrants, you start thinking, well, OK, but if I'm going and attacking someone like Google or Grammarly or someone like that, they're probably not going to let me put flag.txt on the server's file system, right? And so there's this fourth quadrant, which is particularly interesting, of validators that you can actually check the vulnerability using evidence that doesn't require target cooperation, OK? And so the three I've put in a box here are ones where you can do so with close to no risk of false positives, right? You can deterministically check them. However, and I was hesitant to whether to even put this box in, because at the time I came up with this talk and put these slides together, we didn't have these. And the reason is that they have slightly higher false positive rates, right? So again, I debated whether to bring them in, but because I think there's a lot of interest in the sort of bug bounty results, we'll talk a little bit about them as well. And so these are ones where you can try to validate things like arbitrary file reads, remote code execution, SQL injection, SSRFs, without having control of the target. Okay? I will say that we're not going to get super deep into this category because I really did want to stay true to the title. I don't want to do false advertising. And if you do want a sort of broader overview of that, I hear that a couple folks I know, Joel and Diego, are going to be doing a talk at the Bug Bounty Village at DEF CON tomorrow, so you can check that out. OK, so let's talk about how we do some of this automated flag planting. Okay? So at base, it's pretty simple, right? If you have something like a Docker container, when you're standing it up, you just add a line to the Docker file that writes the flag into some location on the file system outside of the web root. For SSRF, again, the nice thing about things like Docker containers is that you can control the network topology, right? So if you have your agent sitting on a machine that can talk to the target, then you can attach another web server to the target server's internal network and put your flag there, right? And so now, if the attacker is ever able to read the flag from that internal web server, then that means they must have found a way to get the target to make a request to this internal network, right? And that's sort of a classic SRF vulnerability. Finally, if it uses a database, you can enumerate all the databases that are used by the application, add a new table that contains the flag, and then tell the agent, hey, go try to read this flag out of the database, right? OK, so that's the kind of simple case. Then we have fun things like business logic. Okay? So at the moment, these are manually done. Although I'll mention very briefly at the end, maybe we could actually automate some of this as well, and that would be pretty cool. But if you want to look for these sort of higher level vulnerabilities, then one thing you can do is actually go into the application and start planting them at places where, according to the application logic, you shouldn't be able to get to, right? So these might be things like you have a couple users you create, you set some private fields in their profile to a canary string. If I can ever read that canary string as an attacker, that means I must have found something that lets me access parts of people's profile I'm not supposed to get to. Or you could put it in somewhere in the admin console, put it in hidden resources that aren't supposed to be accessible to arbitrary users, things like that. Okay? And so if you want to think about this in terms of the classic sort of CIA triad, right? Confidentiality, integrity, availability. These sort of canaries are great for uncovering vulnerabilities that result in a loss of confidentiality. Because at the end of the day, they're standing in for some secret information that the attacker's not supposed to be able to get. OK. So now let's sort of start talking a little bit more about these validators that don't require the cooperation of the target. So one of the simplest ones, although turns out to actually not be quite so simple, is validating cross-site scripting. So in principle, this is really easy, right? You ask the model. When it thinks it's found a cross-site scripting vulnerability, you say, great. give me the URL where I can visit, and when I visit it, it should pop up an alert dialog with a message of my choice, right? So you say pop-up alert XSS. Then you visit the URL in the headless browser. Maybe you let the model give you some cookies or browser state so that if it requires login, then the headless browser can reach that logged in state. And then you just look for alert and check that the dialog was triggered on the right host. OK? You can extend this a little bit. So as we started doing this in the wild, we found, of course, you start scanning targets, and they have things like web application firewalls. And the model is actually pretty good at getting around WAFs. It can come up with creative payloads and things like that. But the validator now has to accept maybe things that aren't just alert. So in our case, we also accepted evidence that it could call console.log, right? And so this is actually pretty easy to implement, right? You can do this with a headless browser with Puppeteer and some callbacks that trigger on alert and console log. Okay? There are a lot of subtleties, and I'll go through some fun ways that we messed this up the first 3 times we did it. But in general, it's not too hard. So you can also extend this pretty easily to things like open redirects. So again, the model gives you a URL, maybe some browser state. You visit it, and the validation criterion is that you should start at the target host, and you should end at an attacker-controlled domain, okay? With no user intervention in between, right? And so in our case, we just stood up a kind of dummy server, evil.expo.ltd. And now we can just visit the URL. If we start at the right place and end at the right place, then we found an open redirect. OK, pretty simple. OK, so one of the more complex ones, and I actually kind of enjoy this. There's a category of vulnerability that I think is really cool, which is cache poisoning. And if you're not familiar with this, the idea here is that you've got some caching proxy in between you and the target. And that caching proxy is going to rely on some fields in the HTTP request to decide whether or not the page you're looking for is actually in the cache or not. Okay? And they call those the cache keys. Now, what happens if there are parts of the HTTP request that influence the content of the page you get back, but aren't taken into account by the caching proxy? Well, it turns out that in that case, an attacker can make a request with one of these fields set to a value they control and get that version of the page cached. And then when someone else goes and visits it, just normally, they'll be served the poisoned version of the page rather than the original version they were trying to reach. Okay? So an example of this with denial of service is maybe you find an HTTP header that when you set it to a certain value, the target server throws an error, right? Starts returning an HTTP 500. But the cache doesn't know that that header was supposed to be used as a key. Okay? So now I can visit the page with that header set, get the error page cached in place of the real page, and now all of a sudden I'm trying to visit the home page of some well-known site, and everyone starts getting 500 errors instead. Okay? And so you've effectively taken the site down with one HTTP request. OK. So what I like about this is it's actually something you can really deterministically check for. And it's not easy. The evidence that the model has to give you is somewhat complicated. So you have to get a base HTTP request, right? So this is one that a normal user would make to the website. You have to have some unkeyed field. So this could be a header, a query parameter, something like a cookie, something like that, and a value that will trigger an error. But then you can validate it by basically saying, I'm going to send the base request 10 times just to make sure there's no sort of natural variation in the page. Then I'm going to send the poisoned value. and check that it actually does return an error. And then finally, the real test is if I go and visit that page again without deliberately setting the value that causes the error, do I still get the error page? Was it cached and now serving me an error, right? One small note here, and this is sort of gets into issues of AI safety, is you really want to make sure that you're doing all of this with randomized, what are called cache busters. So these are randomized parameters that make sure that you aren't DOSing random sites on the internet in the process of your testing. So all these are using randomized cache busters along the way. And so just as what this kind of looks like in process, so here the model has figured out that for a certain site, that if it sets x forwarded host to the null byte, right, that all of a sudden, instead of getting back a normal page, it's going to get back a HTTP 500. Okay? So we do our calibration. Great. The normal request gives back a standard 200 response. When we modify that header, it starts giving back an HTTP 500, right? And so we can keep going. We pass the second stage of validation. And then finally, when we try fetching the original page after poisoning the cache, we get back the poison page, not the original. Okay? So I've had to redact some things here because this one actually is not fixed, and it affected a bunch of sites. But this was found by one of our agents in some of the bug bounty stuff. OK. So there are other kinds of validators we can do here. So for example, one that actually also has a very low false positive rate, but is not as necessarily exciting to present. You can do things like have the agent visit the site and try to uncover exposed secrets, and then just run them through something like TruffleHog. And the nice thing about TruffleHog is it has a bunch of its own verifiers built in, where it will go and try to make an API request given with the leaked secret, and then tell you if it's real or not, right? So we can do those as well, and that also lets you find things like exposed secrets using AI agents. OK. So one thing to kind of think about here is why does validation work, right? So why is this, for example, better than maybe just running some kind of DAS tool across the internet and then trying to do some of these validation steps? So the answer here is that we can actually be very specific about the sort of evidence we require, and then trust that the LLM is going to do the work to translate the specific vulnerability that it has and produce the evidence in the form that we want. Okay? So an example here, and this is using one of the more heuristic validators that I said I wasn't going to talk very much about because they still have some false positives. So maybe the agent says that it found an SQL injection vulnerability. Okay? So a classic way to test for this is you can use SQL injection to make the database sleep for a certain amount of time. Okay? And so in this case, we can ask our AI agent to give us 2 HTTP requests, one of which sleeps for 1 second, one of which sleeps for 5 seconds, and then do a bunch of, make those requests ourselves a bunch of times, collect timing measurements, and gather statistical evidence that this really does differ by the expected amount. Okay? Now, again, SQL map can do this kind of thing, right? It can do these sort of timing-based tests. On the other hand, what if you found an SQL injection in some sort of field that had some extra layer of encoding that the SQL map authors didn't think of, right? For the LLM agent, this is no problem, because it can just base64 encode the parameter and then hand you the requests, right? And so that's the extra layer of flexibility that lets it translate between the evidence that you need and the vulnerability that it has in hand. Okay? We can also make some design decisions here that affect our rates of false positives and false negatives, right? And there's always a little bit of a trade-off here. So If, for example, we want to find arbitrary file reads, with higher false positives, we could just say, give me an HTTP request that returns etsy password. If we really don't want very many false positives, we can instead say, give me a Python script that takes an argument of an arbitrary file to read. And then the LLM will have to give me something that can read arbitrary files. But there's the risk that maybe it messes up writing its Python script. And that's the step that it can't do. It found a real vulnerability, but it couldn't prove it to you. OK. So we ended up with some interesting bugs when finding these validators, one of which, and a lot of this comes down to the fact that LLMs really, really want to please you. And they really, really want to find the vulnerability. So this isn't as big a problem for canaries. But if you don't get your validator quite right, they will start cheating all the time. So the first time we did our XSS validator, I specifically forgot that you could change the URL scheme. And so it just went to JavaScript alert. Great vulnerability. No. The second one was a little more sophisticated. We were trying to make sure that we didn't miss any vulnerabilities. And so we turned off same origin policy enforcement in the browser. The model figured out that it could rewrite the history of the page to make it look like an alert was being triggered on the target when it was really being triggered on a host that the model controlled. Right? And ta-da, there it goes. It went to its own hosting page and got the flag. Things can get really absurd with these. So in this case, we were allowing console.log. And the model discovered that the web application, for some reason, was logging the number of path components in the URL. Just that was what the application's normal behavior was. And so it said, great. I just have to put 666 slashes at the end of the URL, and I'll get the flag. And there it is, right? So you have to be careful about constructing these. One way to get around this is you can use some of the console methods that are less commonly used in web applications, like console.table. OK. But so then we set this loose on the internet. And we did this by scanning Docker Hub for things that looked like web applications. And we got a bunch of features and then derived a bunch more by passing them through a language model to tell us, say, does this thing look like a real web application? Is this just someone's random student project? Does this make sense for the attacks that we want to try? And then went through and automatically synthesized Docker Compose files. So we were also able to do things like provide them with source code because we could give them the file system of the image, which was pretty neat. And so we ranked them. We ended up with a set of something like 60,000 candidates that we wanted to test. From those, we were able to synthesize 17,000 web applications that we could stand up and plant canaries in. And then we attacked each image 100 times for each of these vulnerability classes. And out of this, we ended up with 174 vulnerabilities that we have reported so far, 22 CVEs that we've been issued, and another 154 that are pending there. And just as a sampler, we found things like remote code execution in Apache HugeGraph, PuppyGraph, PDFtron path traversal, some cross-site scripting in fairly well-known projects like JSPWiki and Tomcat, a cool auth bypass in this project called Schooled. And what turned out to be one of the more difficult things is finding all the maintainers and reporting things. So we actually still have a backlog of around 650 things that we need to finish reporting, but it takes a lot of manpower to figure out who to tell and then track that through the whole process. So this is a chart. I'm going a little bit quick now because I want to make sure we get through all these things. But we've got vulnerabilities reported by class. As you might expect, we find a lot of cross-site scripting because It's just really easy to make that mistake. But we also find a lot of fun stuff like arbitrary file reads, remote code execution, path traversal, some SSTI, some SSRF. OK, so because we're short on time, I'm going to just go through one of the 3 case studies in our sort of trophy case, which is this cool authorization bypass that we found in Redmine. And this was fixed a few months ago. But the way we set this up is we took this project tracker. It's written in Ruby on Rails. And we went and planted a bunch of canaries in it in various places. So we created a secret project that was only visible to certain users and put a flag in its description. And then you can see we ended up planting 6 different flags there. And this wasn't too bad. This was like I took an hour out of my day and when pasted CTF flags into this application. And then we told the agent to go and look for it. And it actually did a pretty good job of taking advantage of some of the source code that we had for the app, looking through and saying, oh, OK, well, if I'm trying to read the description of a project, then maybe I need to go through this project query controller. And oh, hey, there's this admin projects field. And if I set it to 1, based on the code, it looks like it'll just list every project, not just the ones that I have permission for. And lo and behold, turns out if you do that, so this is without that flag, then you add that flag, and all of a sudden you can see secret projects that you weren't supposed to. OK, so super cool that we were able to find this completely automatically with just a little bit of setup effort of planting some canaries. OK. So I'm going to skip past a couple cool SSRF in Apache Druid and a fun arbitrary file read and map proxy. The map proxy one, just between you and me and the 1,000 people in this room. This one's not actually fixed yet, but they didn't respond for several months. And so here you go. Here's a vulnerability. OK, so we still have limitations here. Right? It's not a panacea. We do still get some kinds of false positives. It turns out there are some applications where being able to read any file on the server actually intended behavior. At first, I thought, how could this be? And then I saw, oh, OK, this is actually a network-attached storage web application. You're supposed to be able to read the whole hard drive. Nope. The other thing is that some vulnerability classes are really hard to validate automatically. If you think about things like IDORs, business logic, it's hard to think of how you can do those completely automatically. But maybe one thing we could do is instead plant these kind of flags using agents that say, OK, I'm going to go explore the application and try to put these flags in there. OK, so hopefully I've given you lots of good reasons not to trust language models when they tell you there's a vulnerability. But there's still some hope, because there are a lot of things that we can deterministically verify. And that by doing that deterministic verification, we can really scale this process up, find tons and tons of cool vulns. So huge, huge thanks to my colleagues, in fact, several of whom are sitting right there in the audience and did much of the work that I'm talking about. Black Hat only lets one person or a couple people up on stage, but really this was a big team effort, and I'm super excited to work with such great people. So thanks very much, and we have 10 seconds for questions. OK, yeah, so I think we don't actually have time for questions. But we're going to get out of here. I'm going to be over in the wrap room if you guys want to come talk.